Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The afternoon session of our workshop. The first speaker is Brendan McMahan from Google, and he'll be telling us about delay-tolerant algorithms for asynchronous distributed online learning. Thanks, Brendan.
Hi. Yeah, this is joint work with my colleague Matt Streeter when he was at Google. So I'll start out with a very short summary here. So if you remember one thing from this talk, this is probably the thing to remember. And that is if you're going to run asynchronous online gradient descent with massive parallelism, you should choose your kind of per coordinate learning rates very carefully, because that parallelism is really going to change the story here when it comes to learning rates. If you remember two things, you should remember the first thing, and you should also remember that we have a cool algorithm that addresses this problem in a principled and provably efficient way. Okay, so what's the class of motivating problems here? A problem I've worked on a fair bit in the past is add click-through rate prediction, and I think this is a kind of canonical example of a web scale prediction problem. So you might have actually a pretty simple model here, so you can think of something like a large sparse logistic regression, but with a billion-dimensional feature space, right? But for any particular example, you're going to only have 10 or maybe 100 some features that are present, features that are non-zero. So that could arise if you have, for example, bag of words type representations or indicator variables on pairs of words, things like that. So some of those features are very common, and some are very rare, right? You're only going to see them in 1 in a million training examples, but the presence of that word or that feature could still be very important. So this is exactly the kind of data set or the kind of learning problem where adaptive gradient or AdaptiveRevision methods have been shown to be extremely effective. So we're going to kind of build on that same setting, but we're interested in then kind of extending the algorithms to explicitly take into account the fact that if you're going to run on these truly massive data sets, you probably need a massive amount of parallelism as well. And obviously here, any query that's done on Google produces potential training data for this problem. So clearly, it's a large-scale problem. Okay, so here's the slightly longer summary, focusing on this adaptive revision algorithm that I'm going to be talking about. So this is a gradient descent algorithm. We kind of stated and analyzed it in the online convex optimization framework, but optimizing, say, a logistic regression model naturally falls into that framework. It's designed for asynchronous lock-free updates in the spirit of the hog-wild algorithm. In particular, we're focusing on the case where we have very large update delays due to massive parallelism. It's going to adapt to the gradients on a per-coordinate basis like a standard AdaptiveRevision algorithm. But the key difference is we're not going to just do that kind of adaptation, but we're also going to adapt to the actual sequence of delays that occur on a per coordinate basis, right? So this is again a different flavor of data-dependent adaptation. So we're going to prove some strong data-dependent regret guarantees for the algorithm, and we show empirically that you can get an order of magnitude kind of additional parallelism without any cost in accuracy using these methods. So you can massively scale up the number of machines you're using to optimize this problem, and it doesn't cost you anything. Okay, so I'm going to introduce the setting first and talk a little bit about the model for parallelism that we're working in, and then spend actually probably a decent chunk of time on some intuition and theory for an algorithm we can't actually run. And then I'll introduce the actual algorithm that we can run, and there's a fair number of details that I'm just going to gloss over in getting from the hypothetical algorithm to the actual algorithm. And then hopefully we'll have time to talk about experimental results, which I think are quite nice. So here's the picture, and we're going to focus on a single parameter, a single coordinate in this billion-dimensional space. There's what we're going to call the updater, which is a parameter server type representation specific to that coordinate, and it kind of serves that model coefficient to whatever readers need it. So the reader is the thing that's kind of actually just computing gradient. So it reads a training example, computes some features, then it goes to the relevant updaters and requests those coordinates, those coefficients, for those coordinates. Once it's read them, it can compute the gradient, and then it sends the gradient back to the updater in order to take, say, a gradient descent step. Of course, the trick here, and you can kind of see in this diagram, is that in the time between when that read occurred and when the update is actually applied, a bunch of updates may have actually come in. So when you go and kind of apply the update G3 here, the blue update, it was based on reading x1, but the coefficient has actually been updated since then. So this is kind of a delayed and stale gradient, which is exactly what makes this, this challenging. But we need to deal with this problem if we want to avoid locking, if we want to run things kind of as fast as our hardware will allow in a purely asynchronous way. So what does the online gradient update look like here? Well, I'm going to make a couple of very important simplifying assumptions. We can use kind of a standard reduction that lets us assume we're working with linear loss functions. And then we're going to assume kind of an unconstrained model space. And those two things combined mean that we can essentially really do our analysis on a per coordinate basis. And that's important for two reasons. One is it simplifies the notation and the analysis a fair bit. But because we're not assuming that those different coefficients are stored even on the same machine, things kind of can get out of sync in different ways on different coordinates. So just reasoning about kind of that combinatorial explosions of different interleavings of operations would be extremely challenging unless we can, if we couldn't make this kind of per coordinate assumption. But it turns out that the thing that helps with the analysis, even in the non-parallel case, actually gives us a much more powerful result in the parallel case because we don't have to make assumptions that everything is happening in the same order across all of the different dimensions. The next kind of little notational trick is that we're going to index things by the order of the updates. And when you do that, then your gradient descent update looks exactly like the standard gradient descent update, right? xt plus 1 equals xt minus the learning rate a to t times the gradient gt. The key difference here is gt now is not the gradient of the loss function at xt. It's the gradient of the loss function computed at some stale point, right? So you actually saw that loss function a while ago with some possibly stale and inconsistent coefficient vector. You made a prediction, and now at a later date you're actually getting to apply the update. So it turns out the key thing is going to be how we choose those per coordinate learning rates. So here's the intuition, and this is actually, I think, kind of high on that list of things to remember, because you don't have to really think too much about the math for this to make sense. Say we have, m equals 1,000 machines processing data. Right? And now remember, think about this add CTR click-through rate prediction problem. Right? Some of those features are very rare. So consider a feature that only occurs on a p fraction of the training examples. Say a word that occurs on 1 in a million examples. Well, then the effective delays that any given coordinate are going to experience aren't that equal to m, that 10,000 machines you've got working on this. The effective delay is only going to be p times m. Right? Because what we care about is how many updates come in between the kind of read of that coefficient value and when that gradient comes back. And if you've got a really rare word, it's very unlikely that any other updates come in between. And so the effective delays are much smaller. On the other hand, if you have kind of a common word or a common feature, then the effective delays are going to be much larger. Why are larger delays a problem? Well, kind of standard analysis shows that effectively larger delays mean that you have more danger of online gradient descent kind of overshooting. That's really why these delays hurt you. You're just not reacting quickly enough. And the way to kind of get around that, prevent that overshooting, is to use a lower learning rate. So this feels similar to the standard adaptive gradient observation that common features should have learning rates that decrease more quickly. But that effect is actually amplified in a kind of additional way in the parallel setting. And so the question is how to take advantage of that. All right, so the standard AdaGrad algorithms use a learning rate that's like 1 over the square root of the sum of the past gradients. The learning rates we're going to study look very similar, but they have this additional term shown in red. So in addition to kind of the current gradient squared, we're going to have a term that looks like the current gradient multiplied by this GS forward. That's actually a sum of gradients. It's the sum of the gradients that are going to be applied after this update, but based on reads that happen before before this update. So you can think of this as the sum of all the gradients that are currently in flight. And we've got some theory that shows that that's kind of exactly the right way to quantify the impact of these delays, right? If you knew this quantity, this is the type of learning rate you would want to use. Now, of course, this is a hypothetical learning rate schedule because there's no efficient way to know the sum of gradients that are currently in flight, right? If you knew that, you could just kind of apply them immediately. You'd clearly be cheating. So we can't actually use this learning rate, but if we could, it would actually work out nicely. But let me back up. Let me just, to give a quick example of what that forward sum of gradients actually is, right? We can go back to this slide. Here, if we're looking at the update for the red gradient, G2, what's the forward gradient sum for this? Well, it's the sum of gradients G3 and G4, because those are both computed after reading the initial coefficient value x1, but they're not going to be applied until later. Okay. So where did this learning rate formula actually come from? And a little bit of history here. This is actually a very similar analysis technique to the one Matt and I used when we were additionally deriving our version of the AdaptiveRevision algorithm. And I think the phrase in the paper we used was bound optimization. The idea is that we're going to prove a regret bound, which is kind of like a convergence guarantee, that's very general. It's parameterized by the actual gradients you observe, so it's a very data-dependent bound. And it's also parameterized by essentially an arbitrary sequence of learning rates, an arbitrary non-increasing sequence in particular. And once you have that bound, that's a much easier mathematical object to work with than the actual performance of gradient descent. But if your bound is tight, it can still be extremely useful. So the trick then is to kind of take that bound and find a setting of the learning rates that minimize the bound as a function of the actual data you see, the actual gradients. So we do exactly that same thing here, except we use a more general regret bound that actually takes into account this parallelism. And when you prove that regret bound, that's where these forward gradient sums come from. So now we could go about optimizing this bound, and if you've worked with these kind of things before, it should be pretty clear that this is the type of learning rate you want to use. You're kind of trading off two terms in the bound, and so you get this kind of square root of that sum of gradients term. But now we still have this significant practical problem that our learning rate schedule, unlike in the standard AdaptiveRevision case, depends on a quantity that we don't know. Right? So we're really not at all done yet. But this provides some intuition that with a smart learning rate, with smart control of these per coordinate learning rates, you can do something much better. What's the solution? Well, we can't use these forward gradient sums. Those kind of seem clearly hard to track. It's much easier to compute a backward gradient sum. So this is the sum of gradients that were applied while this current update was outstanding, and I'll show you in a minute exactly how we can do a little bookkeeping to compute that. Once we have that, there's kind of two main steps in the analysis. One is to prove that we can kind of plug these backward gradient sums into the learning rate, and that works just as well. But there's a caveat with that initial thing. We can plug in these backward gradient sums, but we still need some backward gradient sums for some future updates that haven't been applied yet. So it's still a hypothetical algorithm. We still can't do it. So the next trick is to say, well, OK, we don't know what the right learning rate to use is now. But again, using, it turns out, exactly the same bookkeeping, we can go back and revise previous learning rates that we chose and essentially use a smaller learning rate. So the idea is initially you take an aggressive gradient descent step, but then you see a bunch of delayed gradients going in that same direction. You say, oh, wait a minute. I probably, if I was going too fast with that initial step because I didn't know that all these delayed updates are coming in. So you actually scale back that previous step. That's the adaptive revision step, and that's kind of the core of this algorithm, where we get the name. So I'm not going to talk through the pseudocode in any detail here. There's the kind of the bookkeeping trick that's called out here. There's the learning rate, which now depends on the product of the current gradient and this backward gradient sum. And then there's an adaptive revision step. So we're kind of maintaining this invariant that this sum of gradients all have the same learning rate, eta old. And so then we can just subtract that off and multiply in the new learning rate. So that's a very efficient step, right? It's not, there's no dependence on the number of gradients in that sum. We can kind of do it all in one operation. So this really isn't much harder to implement than a standard AdaptiveRevision algorithm. There is one cost to running this algorithm that you don't have by running standard kind of asynchronous AdaptiveRevision, and that is in addition to maintaining the coefficient value, like x4 here in the first line, z is like the term that controls the learning rate, so the sum of past gradients squared, something like that. We also keep track of the sum of all of the gradients that have been applied so far. And then what we do is when a reader requests a coefficient value, we send out the coefficient value, but we also send that gradient sum. And then the reader is going to do absolutely nothing with that. It's going to just compute the gradient, and it's going to send that gradient sum back. Right? So we're basically using the network as storage here, but that's kind of a nice trick from a fault tolerance perspective, because we don't have to worry about cleaning up caches when the reader dies or something. It's kind of nice and clean conceptually, and in practice, if your network is fast enough, it's pretty good. So then what's been happening on the updater? Well, before the sum of gradients 1 through 3 had been applied, well, this update was outstanding. Gradients G4 through G9 came in. And so by the time this update from the reader shown here comes back, the updater is storing the sum of G1 through G9. We subtract off the sum of G1 through G3. And what's left is exactly the sum of the gradients that were applied while this update was outstanding, was in flight. So it's a pretty easy trick, but it's also quite nice. And it turns out it gives us exactly the piece we need for the two other tricks in the algorithm. So I'm not going to focus on the regret bound too much here, because I haven't even told you exactly what regret means. The key thing here is that this is basically the kind of bound you would hope to get, right? So we haven't had to make any stochastic assumptions on the data. It reduces to the standard AdaptiveRevision bound in the case that you happen to not be running in any parallelism. And you don't have to tune your algorithm at all to get that, right? Like this algorithm actually is AdaptiveRevision if all of those forward sums or backward sums happen to be 0, which is exactly what happens in the case of no delays, right? So this is kind of a strict generalization of the standard thing that you would probably want to do anyway on these kind of problems. And this also, the bound we get for the actual algorithm, essentially, with a couple of minor caveats, matches the bound you would get if you could run that hypothetical algorithm, where you could kind of know the sum of the gradients that were in flight. All right, so of course the real question is, how well does this actually work? And a little meta point here, anytime you're comparing gradient descent algorithms, you have to be very precise about telling people how you're optimizing the overall learning rate scale factor, right? So I'm going to use these per coordinate learning rates, but I'm going to pick some overall multiplier that I multiply into all of the learning rates across the coordinates. And if you've ever worked with gradient descent in practice, you know that doing that well is really important. Here what I'm doing is the wrong thing. I'm going to optimize the learning rate for each of these problems, but in the zero delay case, and then I'm just going to use that same learning rate as I ramp up the delays. This is all in simulation, so I can control the exact delay pattern. So the constant delay pattern is exactly what you would think. You know, the delays are always exactly 1,000. Everything's in lockstep. The random delay pattern actually doesn't satisfy one of the technical assumptions we need to make, which is why it's interesting to look at that as well. Things still work really well. So the black lines here are kind of the standard asynchronous AdaptiveRevision algorithms, both the dual averaging and gradient descent versions. And what you see here, I mean, the y-axes here in terms of the change in log loss are a huge range, but things are kind of fine up to delays of like 1,000. And you know, I've actually got a paper from NIPS 2013 with John Ducci, and there's a hog-wild paper. A lot of people have observed that the standard algorithms, if you have moderate amounts of parallelism, work just fine. So our experiments bear that out. You know, if you're running on a single machine, 64 threads, you probably don't need this. But there's this real phase change as you get up to, say, 10,000 or delays of 10,000 or 20,000, and you see the standard algorithms are totally blowing up, right? So, like, you know, on the URL data set, you know, we're like 6,000% worse or something like that. So something has kind of gone horribly wrong there. Whereas our algorithm, AdaptiveRevision, is paying a very minor penalty for that extreme parallelism. Okay, so the obvious criticism to that is, well, you weren't tuning your overall learning rate scale factor based on the amount of parallelism. You should do that. Right? And you're right. If you're not going to do anything else, you should at least do that. And so what this plot shows, it's the same experiments, but now kind of for each x value, for each amount of delay, we tune the learning rate separately. And so the bottom plots here show you how the learning rate changes how the optimal learning rate scale factor changes. And what you see, again, for asynchronous dual averaging gradient descent, kind of the standard algorithms, the learning rate scale factor that you should use drops by 2 orders of magnitude as your delays get up to like 10,000 or 20,000. So you're kind of running with a whole bunch more parallelism, but then you're giving back most of that speed up because you're dramatically scaling down the size of the steps you're taking, right? So the algorithms aren't blowing up now. You're maybe 200% worse instead of 6,000% worse. But you're really not taking anything like full advantage of the parallelism. Whereas for adaptive revision, we get a little bit worse, and you can see that you're not getting any benefit from this additional scaling. The learning rates, the overall learning rate scale factor for adaptive revision stays basically the same, with only very minor variation as you increase the delay. So what that's telling you is that we really are taking the delay into account appropriately in these per coordinate learning rate schedules, because additional manual tuning isn't necessary. And in particular, like one point of comparison here, you can see that with a delay of 10,000, so think 10,000 machines processing, producing gradients, we still have better accuracy than the standard algorithms with a delay of 1,000. So that's that kind of order of magnitude of additional parallelism you can afford if you're using this algorithm. So a few quick conclusions. This per coordinate adaptation seems to matter a lot. It matters a lot even if you're not in the parallel case for these large dimension sparse problems, but in the parallel setting it buys you even more. And so you need to take into account both the gradients and the delays, and adaptive revision provides a very nice way to do that. So all in there. Thanks.
Any questions? Yeah, go ahead. Are there microphones anywhere?
Is there any theoretical bound on the number of the machines in parallel we can use? Because I've seen like Hugwild has a bound on the number of the parallel processors, but
You mean like an upper bound?
yes.
I think you could work backwards. Like there's a modest additive term in our regret bound in terms of the worst case parallelism. Did I skip it there? Let's see where did it go. So M in this bound in that additive term is there. So it's those constant terms, or on the inside, you could work out that certainly, if you have as many machines as you have training examples or rounds, that's going to be too much. But it's actually, the upper bound here is pretty large, right? I think if you get lucky with the way things happen, you can use a huge amount of parallelism. I mean, the nice thing to think about here is that the GS, those forward gradient sums, those are signed sums, right? That's not the sum of the magnitudes of those gradients. That's actually the sum of those gradients. So if you get lucky and the gradients are canceling each other out, then you don't really pay any cost for the parallelism. So that kind of tells you that overshooting really is the problem here. If all of those gradients are going in the same direction, and then the next gradient is going in the opposite direction, that's where you kind of pay a big price.
Mm-hmm. And is it over Lipschitz continuous functions?
No, we don't need any. I mean, all we need basically is to have subdifferentials.
Oh. But then, what is that L in the?
We need a bound on the magnitude of the gradients as well. Yeah.
Thank you.
So yes, Lipschitz.
Brendan, you're showing at some fixed time the log loss, right? That was what those graphs.
Yeah, so right. So I didn't tell you exactly what that was. This is actually looking in the online setting. So we're running this online as if it was kind of a continuous setting and making a prediction at each time step. And then after making one pass through the data, we're outputting kind of the average log loss.
I see. So
over the run.
I see. So it's sort of over one pass. Do you have a sense of what the different learning curves for AdaptiveRevision and AdaptiveRevisions look like? In other words, if you actually plot the sort of more traditional learning curves as a function of time?
Yeah, we didn't. I haven't looked at that explicitly. We were really focused on kind of this one pass online setting where I think the kind of continuous validation is the natural metric. But I think if by just comparing points on that curve, you can get a pretty good idea that you're getting significantly more speed up. But we didn't compute kind of numbers in the standard speedup numbers.
Okay, let's thank the speaker again. Okay. So the second speaker of the session is Lihong Li from Microsoft Research, and he's going to tell us about offline evaluation in Contextual Bandits.
Okay, thanks. Good afternoon, everyone. So I'm going to talk about how to do offline evaluation in Contextual Bandits. So what is Contextual Bandits? It's a machine learning model to capture a class of interaction problems that is everywhere in nowadays. For example, users interact with search engine, the operating system, or mobiles or games with big companies. And then in this kind of problems, there is a loop that involves the decision making on the left-hand side and the user on the right-hand side. And this nature makes the problem more difficult and more challenges beyond those arising in pure prediction problems can arise. So when a user comes to the company by visiting a website or using the software or using the mobile phone, the company sees some contextual information about a user, his past, what his query is submitted, the time of day, etc. And then we're going to take actions in the form of showing an ad or a news article or a software component to the user. And in return, we're going to collect some numerical reward from the user, either in the form of clicks, revenue, or adoption, etc. So in this loop, the distinction between supervised learning is that usually when you compare two machine learning algorithms, you try to make your prediction as accurate as possible. So when you try to predict what happens when you show an ad to a user, you try to make the click prediction to be as accurate as possible by looking at log loss. But in this kind of problem, you're actually trying to maximize the amount of rewards in this loop. And these two problems are fundamentally different. And I'm happy to talk about the difference offline in more details. So let me give you a more concrete example of the kind of interaction problems I'm going to focus on today. So this is a module at Bing, the search engine. So as a user, you type a query on the search engine, and when you type too fast, you may have a typo. So for instance, machine learning becomes machine learning, a typo that I make all the time. Modern search engines are smart enough to realize this is a mistake, and then he can correct the typo. So now Bing is showing results for machine learning instead of machine learning. So what the module Speller does at Bing is to detect and correct such typos in the queries submitted by users. And when there's a potential typo, he may generate a subset of candidate queries to be sent to the backend, so that later modules in Bing can retrieve the results and send the right results to the user. And here we want to maximize some click metrics that is well defined. That measures how happy the user is with the final search results. So the user don't see what the speller does. What they see is the final search result pages. So here's some more details about how Bing Speller operates. It's a round-by-round interaction between Bing and the user. When a user comes with a query, then we see a query like Shanghai Pass, and then we send this original query or raw query to Bing, the speller, and then speller may look at this query and realizes that this could be a typo. So G may be missing from the first word, and so Shanghai is the biggest city in China. He may also think that the original query could be right. So Q2, the second candidate, is identical to the raw query, or maybe change the second word from past to past. So Speller has all these candidates, and then he can send a subset of these candidates to later modules of Bing, so that other teams of Bing will retrieve the results, do a ranking, merging to produce the final search results pages. And then we observe whether the user likes it by looking at whether user clicks on some of the articles, some of the URLs, or whether user consumes some of the contents on the page. So in this is a natural problem captured by contextual bandits. So in the terminology of contextual bandits, the raw query that is sent to the input of speller, the decision maker or the learner, is called a context. This is the information that is going to make decision based on. And the subset that speller outputs is called actions. This is what the speller does. And the action affects the final reward because it affects the search result page and affects the user clicks. So the final reward, which is a number, is the number that we try to maximize over time. And then we also call it something called a policy, which is a function that just tell you how to select actions based on the context. So these are all the terminology we're going to need in this talk. And then the fundamental in this kind of contextual bandit problem, like in speller, is to do policy evaluation, meaning that if I'm given a policy that maps context to actions, how do I know whether this policy is good or not? In other words, can I know the average reward the policy collects by running it on live users? And this is an important question. For example, when people decide to ship a new model, then we need to know whether this is a good one before shipping it. And it can also be used as a key step in the more general optimization problem. So in terms of evaluation, we have the two general approaches to do evaluation. The first one is online experiment, meaning that you've had some idea or you have some new model. You can just run it on live users, let it go and see how well it does. And this is essentially what people do in everyday science practice. It's very reliable, but it's expensive. You need to wait a long time. You need to invest a lot of resources to deploy the model on real systems to see how well it works. Also, it could be risky, right? The reason we do evaluation is that we're not sure about the quality of the policy, so it could be risky. Another approach is called offline evaluation, which is my focus in this talk today. Instead of running the policy online, now we try to use historical log data to predict whether the policy is good or not. So this is cheap and fast. Of course, the data is there already, but it's challenging for a reason I'm going to explain in the next slide. So before I'll explain the challenge later in this slide, let me formalize the problem a little bit. So here we focus on stochastic contextual bandits, meaning you don't have to care about the mathematical details here. What it means is by stochastic is that the contexts are stochastic, or the IID. They're drawn ID from some unknown distribution, and then once you have a context, you select an action. The reward depends on the context and action in a stochastic way, another IID way. Okay, so it's not adversarial, it's stochastic, and the quantity we try to estimate is the value of pi, with V of pi, which essentially is just the average reward you're going to collect by running pi on live users. For example, in a recommender system, if you care about click-through rates, then the value of policy could be the average click-through rate if you run it online. Okay, and then if you do offline evaluation based on data, here's the challenge. The data in this kind of interaction problems is usually of the form of context, Q0, the action that you took in the past when you collected the data, and the corresponding reward, R sub A, that depends on action. You're not going to see other actions that are not selected in the past for that context, right? So this is, so in other words, you don't have the corresponding reward signal, R sub A prime, when a new policy selects a different action, A prime, that is different from the one that you have in data. So this is called counterfactual. Well, this is a counterfactual question you try to answer in offline evaluation. So how can we solve this kind of problem? Here I'm going to describe a unbiased offline evaluator for this problem. So the key here is the collection of randomized data. So now before you do an evaluation, you collect a set of exploration data or randomized data in the following way. When the user comes to your website or the search engine, you observe the raw query, and then instead of following the production model to show the same outcome again and again, you will select one of these possible actions with some probability. So this is the multinomial distribution P sub A that you define. So this is a distribution that you can define. It's known, and then you just randomly sample an A from this distribution and observe the corresponding reward. So that's it, very simple. And once you have this exploration data, you can use the inverse propensity score estimator to get an unbiased estimate of the value of the value of the policy that you try to estimate. So what is estimator? It's simply an average over the data set that you have, the exploration data set. Is the average of the reward multiplied by an indicator function, which is 1, when your new policy selects the same action as the one in the log for that context, divided by the probability of A. So this is the number this is a probability you design. This is also known as propensity score in the statistical literature. That's why the estimator is called inverse propensity scoring. So since the A's in the log is selected from probability P sub A, so the indicator function is 1 with probability P. So now divide that indicator function by P sub A, then you're canceling the selection bias, and that's why you can end up with a unbiased estimator using this importance sampling idea. And then this is related, the idea is related to causal inference, covariance shift, and offline, well, off-policy reinforcement learning, as some of you might realize. So back to the bin speller example, this is the pipeline of bin speller. We are trying to optimize the yellow box speller that takes in as input the query and output a subset. So for randomized data collection, we just need to randomize the actions. So we select a random subset for any query and then observe what the user liked the results. And we collected about 50 million search impressions. And here's how it works. So on the left-hand side, you have the position specific click-through rate estimate of the top 8 position on the search result page. So for instance, 1 means that the CTR is the y-axis is CTR, and the orange curve is the offline estimate using inverse propensity score estimates, and the blue one is the actual online numbers that we measure by running a real online experiment. So we are comparing these two and see whether they're close. And indeed, they're very close across all the positions. And on the left-hand side, we have the daily click-through rates. And again, you can see that the online ground truth and the offline estimates based on importance sampling are very close to each other. And this plot shows you that we can also have some kind of have a way to quantify uncertainty in our prediction. So the x-axis here is the key parameter in speller, and the y-axis is a key metric that people care about in bin. And I can't reveal it here, but the higher the better. So by varying this, so people are interested in how the key parameter can affect the key metric. If you do online experiments, every time you can pick a point, you can measure how well the metric is, right? By using the offline evaluation, you just need one data set, and all of a sudden you can plot the whole curve by the whole curve of predicting the online metric by varying the key parameter. So the curve there is the prediction of the inverse propensity score estimates, and then the yellow region is the confidence region. So the wider the more uncertainty there is in the estimates, and the star there is the production baseline, and so you can see that it's very accurate, and indeed the ground truth really lies within the confidence region. And then I just wanted to briefly mention that if you can do evaluation, you can also use that as a subroutine for optimization. So briefly, we train a model to predict whether the user is going to like a correction candidate, and then we can use a fraction of the exploration data to tune some parameter in speller, right? And use the importance, the inverse propensity score to estimate how I should set the parameter to maximize the metrics that I'm interested in, and did it. We did offline experiments and we ran it online, and it did show statistically significant gain. And here's some written example that show how the new model improves upon the old ones. So all this seems good. It seems to be working well. It solves interesting problems. Now we ask the question of whether we can find something that is provably optimal for this kind of offline evaluation problem. So we know that one works, but is there a better one? Or is the boundary a limitation of the hardness of this kind of problem? And so this is some of the recent work. In this work, we take a minimax approach. So here we simplify the problem a little bit. This is just a first step towards solving the whole problem. Here we look at the single context bandits. So we have a set of actions, and then the policy we try to estimate the value for, it's a stochastic policy, and so we just try to estimate the weighted mean. So R is the reward. And then when you have a data set D of size n, you can have an estimate that gives you a number that tries to estimate V of pi. Okay. We're interested in looking at the mean square error of any algorithm, estimator A, and then we try to look at the worst case performance of this estimator within a set of problems constrained by some conditions, like the variance is bounded, the mean is bounded. And then we're interested in looking at the optimal estimator that solved this problem, and we call that the minimax optimal solution. Well, the math may be a little bit complicated here, but at the end, what it says is that we want the best performing worst case estimator. So that's all it says. And then we have a lower bound for this that characterizes the inherent difficulty of this kind of problem. It also gives you a guide of how to define estimators. I won't have time to go into the details of this lower bound, which looks a little bit complicated. What matters is that it consists of two parts. The first part involves the mean square error contributed by not sampling some action in your data set. If an action is not in your data set, then you just don't have the reward signal for that action, and you have to suffer some amount of mean square error because of that. So that's the first part. And the second part related to V1 is related to variance. So when your reward has a high variance, then you expect that the problem is harder. You need more samples to drive the mean square error down to some pre-specified threshold epsilon. Right? So this is what the second part says. And then we look at a few representative estimators and see whether it matches the lower bound. For instance, the inverse propensity score that works well is unbiased, but on the other hand, it turns out to be asymptotically suboptimal, although it's very popular in reality. And then there's another regression estimator. It's slightly biased. I haven't described it yet. It's very simple. I can describe offline. It's slightly biased. And the interesting thing is that it's asymptotically optimal. And with finite time, a finite sample n, we can show that it's optimal up to a factor, a multiplicative factor. However, for a very small sample size, when n is very small, then we don't have a good solution, a way to characterize how it works. So we have some answers to this question, but the picture is not complete yet. And then the analysis we have in this work can also predict what could happen in practice. So this is a plot using data from Bin, comparing different estimators. I won't have time to describe it, but what I try to say is that this plot is consistent with the theory we developed in this analysis. And then and the work on single context contextual bandits also have implications to general contextual bandit and Markov decision processes. Okay, so to conclude, so today I talk about how to do offline policy evaluation in contextual bandits. And then through a case study at BIN, I showed that one of the estimators worked well. And then the next part I show some recent efforts of trying to get the minimax optimal estimator for solving this kind of problem. And we have some surprising findings. In the future, it would be interesting to extend this to large action problems like ranking. When you have many actions, then how can you reduce the variance in this estimator? Also, how can we get a minimax optimal estimator for general contextual bandits? And finally, it would be awesome if we can do offline policy optimization in a reliable way, okay, in a more general, reliable way. Okay, thanks.
Any questions? Yes. Can we get a microphone up there?
Thank you. So my question is regarding basically the probability of action, and you assume at every point that probability of action is known. And so twofold. I can see if the probability of the action changes as the bandit learns, you can have maybe a temporal integration. But what if you cannot know what the probability of action is at a particular time?
That's a good question. So here, when we collect the randomized data, or the exploration data, you design the exploration probabilities, the P sub A's, right? So usually you know that probability. But in some cases, when you don't know, it's still possible to do this kind of thing. The obvious solution, or straightforward solution, would be to estimate the probability from the data. And it's not ideal, but sometimes it works pretty well. So we have a paper in the past that showed how you can do this in a more in a safe way.
Question. So here. So one advantage of doing it in like the speller kind of setting is that you have a very small set of actions.
Yeah.
How do you think this would scale if you're like trying to do actual search? Like you have a lot more actions there because you have a lot more results.
Right, that's a good question. So that's one of the open questions I'm really interested in solving in next steps. And so in general, when you have large actions, and the P sub A's has to be small, right? In this case, when you do one over P correction in the inverse propensity score estimates, and the variance is high. In other words, you need to do a lot of exploration to cover the data, so you have too many things to learn at the same time. So that's the source of challenge in this problem. I think that in general, when you don't have any structure, the problem is hard. We have lower bound, as the last part shows. But in particular problems, specific problems like ranking, I think it's possible to take advantage of structures in problems. Like you have ranking, then it's possible that you can take advantage of the structure in this ranking problem to reduce the effective size of data. So in Wisdom earlier this year, we have a paper that tried to solve this problem, and I think it's along a useful direction. Yeah.
Thanks.
Okay, let's thank the speaker again.
Thanks.
Thank you very much, Lihong. Okay, so now we have a couple of spotlight talks. Okay, so the first spotlight will be given by Wen Wei Loh, and it's entitled Finite-Population Inference for Causal Parameters.
Thank you. So I'm here to talk about my poster. It's joint work with my advisor, Thomas Richardson. So imagine we have data from this randomized experiment. So one example of that would be A/B testing scenario, where we have a randomized experiment Z. There are two values: 1 if an individual is assigned to a treatment group, 0 if he or she is not. We observe a binary final response, Y. So in this case, for example, out of 165 subjects or individuals assigned to the Z equals to 1 group, 90 of them observed, we observed 90 of them having a success. So we could carry out a test for the null hypothesis of whether Z and Y are independent. So Fisher's exact test would be one way to go about doing that. And we get a really small p-value of 3 times 10 to the power of minus 22. Now, what happens when individuals don't do as they're told? None of us actually do. Sometimes we do. So we have a variable x, which is actually the treatment chosen by the individual. right? This takes place after they have been assigned to a particular group. So X is no longer randomized. And as you can see from the Bayesian network, there are personal preferences, for example, H, that may lead to a spurious relationship between X and Y. So now, what are we going to look at? Well, can we still test whether X and Y are independent? Should we test whether X and Y are independent? So in a finite population, which is the context that we're looking at, the set of individuals in our study is fixed. The assignment of the individuals in our study to either treatment, z equals to 1, or control, z equals to 0, is the only source of randomness that we have. And what we do is we propose a likelihood-based approach to test whether X is independent of Y for a selected group of individuals. So if you'd like to find out more about who these lovely individuals are, please visit our poster. Thank you.
Okay, and the second and last spotlight for this session will be given by Safiye Celik, and the title is A General Framework for Meta-Analysis of High-Dimensional Network Inference.
Hi everyone, I'm Safiye Celik from the University of Washington Computer Science Department, and this is a joint work with my advisor, Wen Wei Loh In. In this work, we are introducing a new machine learning framework which aims to integrate multiple datasets into a single statistical model. Those datasets have different sets of variables. So what exactly are we trying to solve? As you may know, genes interact with each other, and many diseases such as cancer are caused by mutations, and those mutations lead to perturbations to the gene network. So one of the fundamental goals of cancer bioinformatics is to understand how those genes are interacting with each other and how they drive the biological disease processes. And the limitation of a standard network inference algorithm is that we have thousands of genes, which means they may interact with each other, and we have millions of variables in the network, and we usually have 100 samples, so patients, which is usually too few to get the underlying network structure. And also it's becoming more common that we have multiple studies and multiple data sets from those studies. So a natural solution is to increase the sample size by combining those data sets. However, different data sets usually do not have exactly the same sets of variables, which makes it impossible to combine those data sets directly into a single model. And to resolve this challenge, we propose the combined module network estimation framework. And we assume that the variables are organized into modules, and those modules have conditional dependencies, so they are interacting with each other, and those conditional dependencies are conserved across the data sets. Many real-world networks, especially the gene expression networks, are known to be modular, and even if the genes are not exactly conserved across the data sets, the biological processes, the modules, should be conserved. That's our assumption. And so Combine leverages this conserved modularity of multiple data sets, which makes it possible to combine these data sets into a modular statistical model. And this also, an important thing is that it's very hard to learn a network of thousands of variables. By using this modularity assumption, we can reduce the dimensionality a lot, which results in an efficient learning framework. In a coordinate descent procedure, we iteratively update 3 sets of parameters. First are the latent variables, each corresponding to a module. And the second is we are updating the assignments of variables to modules using by minimizing the Euclidean distance in an iterative procedure. And the third set of variables is the conditional dependency structure. For this step, we can use a regular like graph learning algorithm like graphical lasso, you may know. And in our experiments on simulated data and ovarian cancer gene expression data, we show that the network learned by our combined model can fit unseen data better in a cross-validation setting. And also the discovered modules have much more significant overlap with the known functional gene categories. And we also use this Cancer Genome Atlas project for ovarian cancer data. And we show that the combined latent variables are much more significantly associated with important histopathological phenotypes. And we also show that the subtypes, the patient groups learned by combined latent variables, better reveal the genomic abnormalities of the patients. If you want to learn more, please come see my poster in the evening. Thanks.